Hello. This time I'm going to explain section 3.8 homework assignment. Section 3.8 is about the derivatives of the inverse function and also derivative of the logarithmic function. Okay, so there are 27 problems here, but compared to section 3.7, each problem is kind of doesn't take much computation and we can finish it probably faster. Okay, let's start from question number 1. So number 1, you have a function, a linear function, fx is equal to negative 6 over 7x plus 6. So first question, you need to find the inverse of this function. To find the inverse of function, this is a reviewing. So original function is y is equal to negative 6 over 7x plus 6, which is a linear function, and the graph looks like something like this. Slope is negative, and y-intercept is positive 6. Okay, so this is a one-to-one function. It passes a horizontal line test, which is at any given height, the horizontal line only meet at the line at only one point. So this has an inverse function. Inverse function is you switch x and y. You got its inverse is you replace input and output. So it's going to be x is equal to negative 6 over 7y plus 6. And you are going to solve for y. So let's multiply both sides by maybe 7. Or maybe just move 6 to the other side. So it's going to be like 6 over 7y is equal to minus x plus 6. Multiply both sides by 7 over 6. So it's going to be 7 over 6 negative x plus 6, which is same thing as negative 7 over 6x plus 7. Okay. So this is the inverse function. This is the input of the inverse function. This is output of the inverse function. So we can rewrite it as the output of the inverse function is negative 7 over 6x plus 7. Just for a quick check, when input for this one, when input is 0, output is 6. For this one, if the input is 6, output is 0. So 1 point is not sufficient to check, but I think for this question, it's good enough. Okay, number 2. So what is the graph of the fx and f inverse x? So f inverse x is have a negative slope with y-intercept slightly over the blue one. So it's going to be here, but the slope is slightly steeper than blue one. So it's something, well, you know, it's x-intercept is 6 or something like this. Okay, and remember, the graph of the function f and the graph of function f inverse is always symmetric with respect to the line y is equal to x. Okay, so the only one with a symmetric one is b and d, but the d looks the best choice. Okay, finally, the last question says, what is the df dx at x is equal to 1? Well, no matter where x is, the slope of the line is the derivative of the linear function is just a slope. So it is negative 6 over 7. Okay. And what is derivative of f inverse at x is equal to f of 1? Yeah. Well, this means well, f of 1 is a y value here, which is kind of complicated value. But remember, slope. This means just the slope. Find the slope of the tangent line, but if the original function is line, derivative is just the slope. So the derivative of this one is negative 7 over 6, no matter where it is. Okay. Now, one thing you want to understand in this section is slope of the original function and the slope of its inverse is just a reciprocal to each other. Okay. Let's move on to the next question. Now you have a quadratic function. quadratic function with a restricted domain, 3x squared with the domain is x is greater than or equal to 0. So quadratic function in general does not have an inverse function because it is not a one-to-one function, which it passed the horizontal, it failed the horizontal line test. The horizontal line meets at the two different points. However, if you restrict the domain to the positive side only, then this is a one-to-one monotonically increasing function. So this has an inverse, okay? To find the inverse function, let's rewrite this one as y is equal to 3x squared. And so its inverse must be x and y replaced. So x is equal to 3y squared with the fact that y must be now greater than or equal to 0. So divide both sides by 3. And so for y, you want to get the plus minus 1/3 x of the square root. Although this is going to be plus minus here, because y is positive, because originally x is positive, so you want to take only a positive side. Okay. Now, graph of this one is, even if you don't remember how to graph the square root function, the graph of the inverse must be symmetric with respect to x is equal to y here. So the graph looks like this, okay? Symmetric to the original function. So the only choice, well, first of all, the blue one is incorrect in most of them. The best, only choice looks good is A. So A is the best choice. Okay, now second part is find the slope at x is equal to 3. So let's differentiate the original function, which will be 6x. So to find the slope at x is equal to 3, you got 6 times 3, which is 18. So slope at this point is 18. Now you are asked to find the derivative of the inverse at x is equal to f of 3. Okay. So this, we don't know what this point is, but you know, after you calculate it, it's 7, 3, and 27. And you want to find the slope of this point, which is 27, 3. Okay. And you don't need to do any computations if you know the slope of this black one at 327, because slope at this point is just a reciprocal of this one, just like we did it here. Okay. So the slope of this one corresponding to this one is reciprocal, which is 1/18. Okay, now more than it's more complicated than the quadratic, which is a quartic function. So f of x is x to the fourth minus 3x minus 2380. And it said that x is greater than 3/4. And what this means is, well, this function is itself is not a one-to-one function. It does not have an inverse because, you know, considering the fact this is a quartic function, it's coming down, I mean, coming from left end to like going down and going up, this kind of graph. So it is not a one-to-one function. However, by restricting to this part, you probably only see this part, only the increasing portion of the graph. So there will be some inverse function. You don't have to prove why x must be greater than this specific value. You will need the technique of the derivatives, which will be learned in chapter 4. But anyway, so I need to find the derivative of the inverse, but let's find the derivative of the original function. Okay, so derivative of the original function is 4x cubed minus 3. That's it. Okay. Now, let's actually evaluate what the slope adds. So you have an original function and you have an inverse function. Okay. Now you want to find the slope of the inverse function when x is 0, okay? When x is 0. And it says 0 is corresponding to f of 7. So that means the original function goes through the point 7, 0, okay? And the inverse function must go through 0, 7. Now, slope at this point must be a reciprocal to the slope at this point of the original function. So we just need to find the slope of the original function when x is equal to 7. So let's find f dash of 7, which is 4 times 7 cubed minus 3, which is 4 times 3, 4, 3 minus 3, which is 1, 3, 7, 2 minus 3. So the slope is 1369. Okay, that's quite big. Okay, so once you find the slope of this blue line at x is equal to 7 is 1369, then the slope of the counterpart of the reciprocal function, inverse function, the slope of this red line must be reciprocal to this. So that's why the answer is slope at this point is 1/1369. Okay. Okay, this is just a review question. This question is just asking for, are they inverse to each other? The answer is no, because the graph is not really symmetric. Blue and red one is not symmetric with respect to the line y is equal to x. It is symmetric with respect to the origin though, but it's not a line symmetry. So the answer is no. Okay, from here, mostly we want to just do derivative of the log function. So here's a formula you have to memorize. Derivative of ln x is 1/x. If you combine the chain rule, the derivative of the ln u is equal to 1/u times u dash, which is u dash over u. Okay. So now let's do this one. So y is equal to ln of 9x plus 7x. So y dash is equal to, use the chain rule, u and u dash plus derivative of 7x, which is 7. Simplify this expression, you want to get 1/x plus 7. Okay, so that's number 5. Number 6. Y is equal to ln of t to the power of 9. So let's differentiate y with respect to t. So use a chain rule, u on the bottom and u dash on the top, which simplifies to 9/t. If you remember the property of log, you can first rewrite this expression into 9 times ln of t. After that, you can differentiate to get 9 times 1/t, which is 9/t. This might be faster sometimes, okay? So try to review the property of logs whenever you have some time to do it. Okay, next one, number 7. So y is equal to 3 times ln of 16/x. So inside the log is kind of complicated, but let's differentiate directly. So it's going to be 3 times u on the bottom and the derivative of u on top, which is negative 16/x squared. Bit complicated. It's a fraction inside a fraction. So let's multiply top and bottom by x squared. So you want to get 3, 16x, and negative 16, which simplifies to negative 3/x. Quite simple, right? Now let's use some log properties to simplify the expression before differentiate. So this is the log of the quotient. So this can be written as 3 ln 16 minus ln x. Okay, now let's differentiate this one. Let's expand this one first. So because it's easier to understand. So let's expand this one. So forget about this dash, it's still y. Now, when you differentiate this one, notice this is just a number. It's just a constant. So derivative of this part will be 0. And the derivative of this is going to be 1 over x. So it's going to be minus 3 over x. Okay. So if you understand some properties of log, sometimes the calculation become much faster, much simpler than if you directly differentiate this stuff. Okay. Number 8. Now you have a trig function inside log, but the idea is the same. So y dash will be constant times u on the bottom and u dash, which is same thing as cotangent. Okay. Okay, this is again a review question. Question is just write exponential expression in to a log expression. Okay, so let's put both sides of the expression into any log. For example, let's put into ln, or well, in this case, base is 256. So let's put into the base 256. So log of base 256 of 4 is equal to log of base 256 of 256 to the power of 1/4, which is same thing as 1/4. Okay. So the final expression is 256 log of 4 is equal to 1/4. Okay. Okay. Now differentiate ln of x to the power base. But this is quite simple. Just differentiate using a formula. So u on the bottom, u dash on top, and simplify the fraction. Simple. Number 11. A bit more complicated expression, x to the 4th times ln of x times, so you have to use the product rule, be aware of that, to the power of 6. Okay, remember u to the 6th, derivative is 6 u to the 5th times u dash. So y dash will be 6 times whatever inside to the power of 5. Up to here is okay. Now you have to multiply it by chain rule, the derivative of the inside, not the derivative of the inside, which you have to use the product rule.左微分 times 右 plus 左 times derivative of the 右. Okay, so that's it. Okay, of course, you can factor this one. First of all, this part become x cubed. This part become x cubed, and you can factor out x cubed out. So the better solution is 6 x cubed, x to the 4th, ln x to the power of 5, parentheses, 4 ln x plus 1. Okay. Number 12. ln of 9x over 9x. What rule we can use? The quotient rule. Do you remember quotient rule? It's gonna be the denominator squared, 上微分下 minus 上下微分. Okay, so we wanna apply that rule. So denominator square. So numerator differentiate u dash times star minus 上下微分下微分 okay, so this becomes 9 minus 9 times ln of 9x over 81x squared. Of course, you can factor out 9 on the numerator, and you can reduce the fraction to make it to 1 minus ln of 9x over 9x squared. So that's a better answer than the one I wrote on the left because it's not in the simplest form. You can divide top and bottom by 9. Okay. This is a challenging one. You will have to use chain rules multiple times. So number 13, fx is equal to ln, it's not the product, ln of ln of ln of 12x. Okay, so it's not the product here, it's a composition of multiple functions. So remember that ln u derivative is u and u dash. Okay, so f dash x is, it's basically derivative of the ln function, it's just a single ln. So it looks like ln of something. So derivative of some that is equal to u, which is inside, 1 over u times the derivative of the inside, which is derivative of this one. Again, derivative of this one is, looks like ln of something, right? So it's gonna be u, 1 over u times derivative of this one. And derivative of this one will be 12x, u, and u dash. That makes sense? So in the first part, you are actually using this part as u, okay? And I'm using a derivative of ln u as 1 over u times derivative of the u. So this part is u, this is 1, and this part is u dash. Okay, and the derivative of this blue one is derivative of ln of something, right? So now you are substituting this part. So you are basically working with ln of u, or let's say the ln of v, or just give a different name, and you're just applying the same rule twice. Okay. Next one, another quotient rule seems to be enough. So y is equal to 2 plus ln of t over 7 minus ln of t. So you have t on top and bottom. So you want to use the quotient rule. So the denominator square, you don't need to expand. Derivative of top gonna be 0 plus 1 over t. 上微分下マイナス上下微分 gonna be 0 minus 1 over t. Okay, this is not really in the nicest form. You have a fraction inside a fraction. So let's multiply top and bottom by t to eliminate this one. So it's gonna become 7 minus ln t minus 2 plus ln t over t 7 minus ln t squared. Denominator is in factored form, so looks nice. Numerator is not the factored form, and it can be simplified by combining like terms. So it's gonna be 5 minus 2 ln t over t 7 minus ln t squared. So you are expected to simplify to this part. Otherwise, you might lose a point. Okay. So the Pearson does accept this terrible, incomplete, not the simplest answer. like this one here, but in like a Japanese program book or in any math test, that you will not get the full credit for this solution. So be careful about this. Okay, this one is very similar to the one before, which was about number 13, ln of ln of ln of something. So it's a kind of composition of ln 3 times. Now you have just a secant in between, but it's still just the compositions. So y is equal to ln of secant of ln of 10 theta. Okay, so the derivative gonna be, so dy d theta is equal to derivative of ln something. So it's gonna be 1 over something, just copy it, times the derivative of this inside, okay? So it's just like 1 over u times u dash. Now I'm gonna focus on this part. So this part is derivative of secant. Derivative of secant is secant whatever, tangent whatever, times derivative of the inside function, okay, by the chain rule. So what I used is secant, secant u's derivative is secant u, tangent u, and u dash. Secant u, tangent u, u dash, okay? So one last thing is just the derivative of this part, which should be easy. So the final answer will be 1 over this junk times secant something tangent something times derivative of this one is going to be 10 theta 10, which can be reduced to 1 over theta. Okay, so looks complicated, but basically using the chain rule several times. Okay, this is just a review question. I'm not going to explain much. More just what this means is, this is same thing as log of base 2 of 2 to the power of negative 3. So it's going to be negative 3. Or you can use like this, ln of 1 ln of, not ln, log 2 of 1 minus log 2 of 8 by changing the division into difference of log. And this is 0, and this is 3, and you want to get negative 3. Yeah, there are several ways to get the same conclusion. So let's move on to the next question. Okay, now you got something new here. They use logarithmic differentiation to find the derivative of y. This is some technique. In Japanese, it's called 対数微分法。対数微分法ですね。So here's the idea. When you have like a product of many stuffs, or power of many stuffs, it's kind of very difficult to differentiate this expression because derivative of the sum is easy. Derivative of sum is easy, just take a different derivative of each, but the derivative of product is complicated, like this. When you have derivative of the many product, then it's gonna be more complicated, right? So to avoid such computations, when you have like a product of bunch of stuffs, one technique to do is actually taking a log. Okay, well, here's one idea. First of all, this is one idea you need to use. Well, ln of absolute value of x gives you 1 over x when you differentiate it. So it's really absolute value does not change the result of the differentiation. So what you want to do first is you want to take a derivative, you want to take an absolute value on both sides of the expression if that is not necessarily positive. Otherwise, you cannot plug in into log. Now, both of the expression is positive, if not 0. So you can put into ln. Okay. The reason for putting into the ln is because ln break down the multiplication into the sums, which is significantly easier to differentiate because you just differentiate each part and you want to take a sum. So this idea, putting into log and divide it into sum or difference, that's the idea of the logarithmic differentiation. Now, once you get this point, use the idea from the previous section, which is differentiate both sides of the expression with respect to t. So you want to get the y on the bottom and y dash on top by the chain rule. And the derivative of this one going to be 1 over t plus 1 over t plus 4 plus 1 over t plus 7. The derivative of bottom is top. Okay. Now to find y dash, you multiply both sides of the equation by y. You want to get this as a final answer. Okay. Of course, you don't want to have an answer in two variables. So rewrite y into the original one, which is this. So y dash is t times t plus 4 times t plus 7 times 1 over t plus 1 over t plus 4 plus 1 over t plus 7. Okay. So differentiation is done by this point. Of course, you can simplify this expression. And in Japanese problem book, this is considered as like a kind of incomplete solution. And you are expected to combine these fractions and multiply it out. But for this one, I believe this is good enough. I think this is good enough. We can move on to next question. Okay. Okay, again, you got a bunch of product or quotient. Okay, so you have y is equal to 1 over t plus 8, t plus 2, t plus 9. Let's take absolute value first to make sure this can be put into the log, and you plug in into log. Okay, now this can be written as minus ln of t plus 8 minus ln t plus 2 minus ln t plus 9. Then again, differentiate. You want to get y dash over y is equal to minus 1 over t plus 8 minus 1 over t plus 2 minus 1 over t plus 9. Okay. And after that, you multiply both sides by y and rewrite y into this, and you got the solution like this. Okay, number 19. This is just a review question. You have to solve for this exponential equation. To solve for x, you have to use log in general. So you plug in both sides of the expression by log. The base is actually any base is okay, but I recommend you to put into ln because in calculus, most of the time, you prefer to use ln as a base. I mean, ln as a log, best log, okay? So property of ln, log, use this x move out to the front. So x times ln of 4 is equal to ln of 10. Well, ln of 4 is just a number. Divide both sides of the equation by ln of 4, you get ln 10 over ln 4. You cannot simplify this 10 and 4 because they are inside ln function. But for this question, you just plug in into calculator to find 4 decimal places. Okay, I don't have a calculator, so just stop here, but you should be able to get the answer. Okay, this is just a review question, which I have already done it several times. Just rewrite it into the difference or sum of the logs. So just for reviewing, this is just reviewing. Remember 3 things. when you have m and n product of ln, then it can be written as the sum of the logs, assuming they are positive, okay? When you have a quotient like this, you can written as the difference of the log. And when you have an exponent like this, then this become a product, okay? So how do we do with this one? So ln of 2 over 3x cubed y is same thing as ln of 2 minus ln of 3x cubed y using this rule. Now you want to use this rule to rewrite this as sum. Be careful that you have to use a parenthesis. So this become ln of 3 plus ln of x cubed plus ln of y. Now this cube is you can bring down to here using this rule. And after you remove the parentheses, you want to get the result. Well, I took several steps, but I hope you can do this in one step from here to here in one step. Okay. Note that this is 2 to the power of 1. Okay. And this is in the denominator, so it means it's 3 to the power of -1. And this is also in the denominator, so it's x to the power of -3. And this is also in the denominator, so it's same thing as y to the power of -1. And you see this corresponding to this one. 1, -1, -3, -1 in the coefficient. And you can just put have a different, sum of the logs. Okay, so I hope you can see this part this way. You can see this way and change it to this. But anyway, this is just a review question. So let's move on to the next question. Okay, number 21. So y is equal to ln of 4 times cosine to the power of 5. Okay, so it's just like ln of u again. So its derivative is u dash. So the u is whatever inside. So 4 cosine to the power of 5. And the derivative of this one on top, which is, so it's something to the 5. So it's going to be 5u fourth u dash. So it's going to be 20 cosine to the power of 4th. And the derivative of the inside of the 5th power, which is negative sine theta. Okay, now you can simplify cosine to the power of 4th and cosine to the power of 5. You can reduce the fraction into -5 sine theta over cosine theta, which is same thing as -5 tangent theta. Okay, is it complicated a bit? You could actually make this simpler. So how do we do it? Before directly differentiate, try to rewrite this expression into sums. You notice that this is just the product here. So if you can rewrite this expression into ln of 4 plus 5 times ln of cosine, then it's kind of much easier to differentiate. So then the derivative of this is just a number, derivative of the constant is 0, and the derivative of the constant times log. So the derivative of ln cos is cos and negative sine, and you want to get -5 tangent. So this is much safer way because from first step doesn't take much time, and the derivative of this is much easier to check that is correct. This is kind of complicated. So when you're working with the logs, try to use the property to rewrite the expression, given expression into something that is easier to differentiate. And easier usually means sums and the difference instead of the product. Okay, so now we're gonna use the same idea for number 22. So 22 is you have a ln of 9t e to the 5t. So using the same rule, you wanna get this is ln of 9 plus ln of t plus ln of e to the 5t. which is same thing as ln of 9 plus ln of t plus 5t. Okay, do you remember? Ln of e is equal to 1, right? And ln of e to the power of x is equal to x, right? So this is just a rule. Because ln is same thing as log of base e, and this is actually equal to x. ね、覚えてるかな? And this is equal to 3, right? なんで、これが2の3乗だからね。2の3だよね。3だよねっていうね。So in general, when you have log of base b of b to the power of x, that's equal to x, because exponent and log are actually inverse to each other. So this part is actually equal to 5t. Now the derivative is easy. Derivative of the constant, derivative of ln t, and derivative of 5t. So it's going to be 1 over t plus 5. Okay, next one. This is actually a very complicated one. This is actually, you need to use logarithmic differentiation technique. Up to now, you have learned the power rule to deal with something like this. When you have a variable on the bottom and a constant on top. In such case, you could use the power rule, which is bring the 23 down and subtract the power by 1. When you have a number on the bottom and x on the top, that's the exponential function. And there is a way to differentiate this one too. It's a derivative of the exponential function. It's basically, you have a same thing, 23 to the power of x, but you have to multiply it by ln of 23. That's a kind of formula. When you have a b to the power of x, its derivative is b to the power of x, but you have to multiply it by ln of b. In case you have e, it's e to the x and the ln of b. But ln of b is equal to 1, so it's become like much nicer than any other basis. So for the polynomials, there is a power rule. When you have an exponent, there's a rule for the exponential functions too. However, how about if you have x to the power of x, when you have a variable on the bottom and a variable on the top? In such case, is there any formula? And actually, there is no formula you have to memorize, but you have to memorize there is a way to deal with this kind of expression. Okay, so this problem, you have a variable on top and a variable on the bottom. To change this expression, you're gonna put both sides of the expression into logs. Okay, so this is, assume this is exponential functions in the bottom. So we assume x and y is positive. Okay. Now, if they're positive, we can put into ln. And the reason for putting into ln is because you can bring this one down to change the problem into the product. So it's kind of complicated, but now you should be able to differentiate this expression in using an implicit differentiation, because it's just a product of two known functions. Okay, now using a product rule, now let's differentiate both sides with respect to x. Okay. So it's gonna be 左微分, which is 3y dash times 右 plus 左右微分. That's equal to 左微分右プラス左右微分は y 分の1 and the chain rule y dash. Okay. Now we want to solve for y dash. But first of all, maybe you don't like fractions. So let's multiply top and, multiply both sides of the expression by xy. Let's multiply everything by xy and xy. So you're gonna get 3xy ln x y dash plus 3y squared is equal to 7xy ln y plus 7x squared y dash. Now this is y dash, this is y dash. So bring this one to the left side and bring other stuffs to the right side. You're gonna get 3xy ln x minus 7x squared times y dash is equal to 7xy ln y minus 3y squared. So y dash is equal to 3xy ln x minus 7x squared and 7xy ln y minus 3y squared. Okay, so that's y dash. So let's see, that's kind of long. 7xy ln x, ln y minus 3y squared divided by 3xy ln x minus 7x squared. Okay, so, okay. Now, terrible question. That's something not so usual to see. You have a log of base other than e. So you got the ln of base 6, which is terrible. So how should we do this? Well, there's a formula. There's a formula for log other than base e. So when you have a log of base v over x, the whose derivative will be 1 over x, just like ln. But now you have to multiply it by ln of b on the bottom. This is a formula. But even if you do not remember this formula, you still can solve this one. First of all, because you don't like this base 6, just put everything, rewrite it into 6 to the power of y is equal to 5 theta. Then put this expression into ln, which is more preferred base. 気に入らないね、ベース6のログを外して、で、再度ね、ln に入れて y をちゃんと下に落とすと。Okay, then you should be able to differentiate this. So let's take differentiation both sides of the expression. So ln 6 times y dash, this is just a number. So number times y. Derivative of this is equal to number times y dash. And derivative of this is going to be 5 theta and 5. The u and u dash, which is 1 over theta. Okay, so y dash will be equal to 1 over ln 6 times 1 over theta. Okay, which agree with this formula. もちろん公式覚えてたらね、そっちの方が早いんですけど、忘れたとしてもね、気に入らないベースを外して再度入れるっていう考え方で解けます。Okay, now another base 5 stuff. I'm not going to explain again. Well, this answer is very terrible, but it's still accepted by Pearson. So this is log of base 5 of x plus log of base 5 of x to the power of 4th. Well, first of all, this is, you can combine them. You can combine them into one log. It's become log of base 5 of x times x to the 4th, which is log of base 5 of x to the 5th. Yeah. Okay. Now, you don't like this base. Do you remember the change of base formula? Change of base formula is log of base b of m can be written into log of base c of m over log of base c of b if you want to. This is called change of base formula. 点の変換公式ですね。点の変換。Right? So, because you don't like base 5, because you don't remember how to differentiate that, So let's change into ln of x is 5 over ln of 5. Looks complicated. It's a fractional expression. However, bottom part is just a number. So it's just like a number, it's just a constant. Number times ln. So that's kind of easy to differentiate. Yeah. So number times the function, that's derivative is the function's derivative times the number by constant multiple rule. So y dash gonna be just a constant here and the derivative of this part, which is u and the u dash, which is 5 over x. So it's gonna be 5 x ln 5. Okay. Stopped. Oh, yeah, the screen is freezing. Okay, again, number 26. So I'm not going to explain clearly. Explain it in detail. How do we differentiate this? Okay, I hate this base. So let's change to ln. Okay. It's not, I don't differentiate yet. Now, numerator is basically just 7x. Remember, that's log of base c of e to the power of x is equal to x. Using this property, numerator is 7x. So it looks complicated, but it's basically number times x. It's just a linear function. So what is the derivative of the linear function? Well, it's just a slope. So the slope is this weird number 7 over ln 2. Okay. One more question. Okay, number 27. Is this an exponential function? Unfortunately, it's not. So it's x to the power of 8x plus 9. Okay, so we can assume x is greater than 0 because it's power of any real numbers. That's kind of, it's only well defined for positive numbers. So we can assume x is positive and the right-hand side is positive. So in that case, let's use logarithmic differentiation technique. Remember, when you have x on the bottom, number on top, power rule. If you have number on bottom, x on top, you got to use the formula for the exponential function. When you have a letter on letter, then you have to use a log technique. So let's put both sides of the expression into ln. Using the property of ln, this power comes down. So the right-hand side become a product. Now let's differentiate both sides of the expression with respect to x. You're gonna get y dash over y is equal to 左微分右プラス左右微分と。To find y dash, you multiply both sides by y and you get y dash. Okay. Now y you can return into this. You want to have answer in single variable rather than combination of x and y. So bring back y into x. The answer is x to the power of 8x plus 9, 8 ln x plus 8 plus 9 over x. Okay. So that's complete explanation for section 3.8. Okay. So it's starting with the derivative of the inverse functions. The derivative of inverse is the slope of the tangent line is basically just a reciprocal of the original function's corresponding point. And also using derivative of the inverse functions, you can find the formula for the log. And most of the problem later in this section is just derivative of the logs. And there are several ideas that use property of log before differentiate to simplify the computation. And sometimes you put both sides of the equation into log to simplify the computation. It's called the differentiation, logarithmic differentiation, 対数微分法. 対数微分法 is very useful when the given expression is a bunch of multi-product or quotient or powers. Okay? 掛け算割り算指数でね、もうガチ頭になっているような式を微分するには、対数微分法、両辺をログに入れることによって、足し算引き算の形にして微分しやすくするというアイデアを、使うことがあります。So, thank you for your participation and see you next time in section 3.9.